Okay, wonderful. So today's lesson is going to be very brief. Most of what I'm going to be sharing today you may have seen before, so I'll make it as brief as possible. Our objectives are students be able to identify reflectional symmetry in geometric figures and the number of lines of symmetry, and students will be able to identify rotational symmetry and its order in geometric figures. Does anyone have any questions before I begin? Questions? So today's is our last lesson in Unit 2, and it is symmetry. And at the end of this lesson, we should be able to answer this question: how can you identify symmetry in a figure? So what is symmetry? Well, we may have learned about symmetry sometime in middle school or elementary school. And so symmetry is basically the property of having an object flipped or rotated or moved to exactly map to itself. There's an implied congruence of sides and angles, which means if there is symmetry, then the angles and sides are congruent. So symmetry looks something like this. Let's say we have the word map. We can split the word or the letter M in half to create two congruent sides. We can split these letters in half to create two congruent sides. We can also split the letter H 2 times, one time vertically, one time horizontally, to create 4 congruent sides. So this is symmetry, and I'm sure many of us know what it means to be symmetrical and what symmetry is. And so here's just an example for those of us who aren't sure. So symmetry, this would not be an example of symmetry because that bottom half does not match that top half. This, however, would be an example of symmetry because we have 2 congruent halves that look exactly the same. And if we were to flip that heart onto each other, then those 2 parts would match up. Okay. So in geometry, there are 2 types of symmetry that we talk about: reflectional symmetry and rotational symmetry. First, we're going to look at reflectional symmetry. Reflectional symmetry of a geometric figure is the characteristic of a figure to map itself across a line of symmetry. So here we have different types of reflectional symmetry. So reflectional symmetry is basically the symmetry that we are used to, lines of symmetry. So you can cut this triangle in half to create 2 congruent sides. There are 2 types of lines of symmetry that we see. We see vertical lines of symmetry, so we can cut that line up and down to create 2 congruent halves, or horizontal lines of symmetry where we can cut a figure from left to right and get 2 congruent sides. Okay. And so I want to ask you guys, which diagram represents a line of symmetry for this pentagon? Is this a line of symmetry? Is this a line of symmetry? This or this? And I'll wait for one person in the chat box. Which of these represents cutting that figure directly into 2 congruent sides? Naomi says B. Anyone else have any guesses? Anyone else agree, disagree? Seems like everybody agrees. And Naomi is correct. That is, in fact, the line of symmetry of this pentagon, right? Because here we have this half does not match this half. These 2 halves are congruent. This half does not match this half, and this half does not match this half. So the only line of symmetry that we see is B. So reflectional lines of symmetry. The number of lines of reflectional symmetry will vary for each geometric figure. So not every figure has the same number of lines of symmetry. A figure is said to have n-fold reflectional symmetry, where n is the number of lines of symmetry. So what this means is, let's say we take this triangle and we find its line of symmetry. Well, this triangle only has 1 line of symmetry, right there. Well, the way that we would talk about this line of symmetry is we would say that this triangle has 1-fold reflectional symmetry. So instead of saying this triangle has 1 line of symmetry, we would say it has 1-fold reflectional symmetry. So that's basically what this is saying. We talk about reflectional symmetry by saying fold reflectional symmetry instead of line of symmetry. Is there any questions about this? And so here's some reflectional symmetries of trapezoids. And again, we're going to see where the word folds comes into play. So here we see this trapezoid. And this trapezoid only has one fold reflectional symmetry. Here we see this other trapezoid. We can see that there's no instance in which we can cut this image in half to create symmetry. And so it has none or zero folds of reflectional symmetry. Any questions? And so the interesting thing about reflectional symmetry is the reflectional symmetry of a regular polygon. Regular polygons are polygons that are both equiangular and equilateral. What does that mean? Well, that means that all the angles are equal size or measure and all the lines are equal length. So for example, we have this triangle here. All these angles are the same and all these lines are the same or congruent. Well, once we know that a shape is a regular polygon, we can identify the number of folds or reflectional symmetry it has. And we do this by identifying the number of sides of that figure. So this triangle has 1, 2, 3, 3 sides. So triangles have 3 sides. Well, because this triangle is a regular polygon, we can also say that this triangle has 1, 2, 3 fold reflectional symmetry. So for all regular polygons, the number of sides tells us the number of reflectional symmetries. So here we have an octagon, and we know an octagon, or here we have a hexagon, Here we have a hexagon. We know a hexagon has 6 sides, and we can count them 1, 2, 3, 4, 5, 6. And because this hexagon has 6 sides, well, we can also gather that it has to have 6 folds reflectional symmetry. So regular polygons with n side will have n folds reflectional symmetry. So if this regular polygon has 3 sides, it'll have 3 fold reflectional symmetry. If this hexagon has 6 sides, it'll have 6 fold reflectional symmetry. If we have an octagon, which is a regular polygon, or octagon has 8 sides, it'll have 8 fold reflectional symmetry. And we can see those lines of symmetry here. Is there any questions about this? And this applies for all regular polygons. And you'll know a figure is a regular polygon if it is equiangular, all the angles are the same, and equilateral, all the line segments are the same. Okay. So here we have 2 types of regular polygons. So I'm telling you off the bat, these are regular polygons. So then what is the reflectional symmetry of this square? Someone want to put in the chat box, what is the reflectional symmetry of this square? If we know squares have 4 sides, what is the reflectional symmetry? Someone want to put in the chat box? Oh wait, for one person. Square has 4 sides. It's a regular polygon. So what fold reflectional symmetry does it have? We're looking for a number. Remember, if we have a regular polygon, we count the number of sides. A square has 4 sides, and so we have 4-fold reflectional symmetry. So the number of sides is equal to the number of lines of symmetry. So you see those there. And so that being said, here we have a regular octagon. This is a regular polygon. We know an octagon has 8 sides, so how many fold reflectional symmetry do we think it has? And I'll wait for one person in the chat box. If it has 8 sides, how many fold reflectional symmetry does it have? Naomi says 8. Does anyone else agree with Naomi or disagree? 8. And Naomi is correct. It's 8. And how do we know that? Well, because octagons have 8 sides, or we could count it 1, 2, 3, 4, 5, 6, 7, 8. And because it's a regular polygon, the number of sides is equal to the number of reflectional symmetry. So if it's 8 sides, that's 8-fold reflectional symmetry. 4 sides, 4-fold reflectional symmetry. Okay, any questions? So I'm going to play a little bit of a video to help you understand rotational symmetry because it's easier to see than to explain. So I'll play this video and then we'll come back.
Welcome to Moo Moo Math, where we upload a new math video every day. In this math video definition, I would like to talk about rotational symmetry. Rotational symmetry is when an object is rotated around the center point a number of degrees and the object appears the same. The order of symmetry rotated around the center point a number of. Welcome to Moo Moo Math, about rotational symmetry. Number of degrees and the object appears the same. The order of symmetry is the number of positions the object looks the same in a 360-degree rotation. This shape has an order of 3. This star has an order of 5. Thanks for watching. Moo Moo Math uploads a new math video every day. Please subscribe and share.
Sorry about that. So a better idea is I'm going to go ahead and show you. One second. Let's see. Okay, and I need to go like this. Okay. So what is rotational symmetry? Well, basically, if we had this figure and we rotate it about a center point, so the center point is always going to be in the middle, well then we'll know we'll have rotational symmetry when this figure meets up back with this original bounds or within these lines. So if I turn this figure 90 degrees, well, we can see it does not match up with those lines. So 90 degrees is not this figure's rotational symmetry. If I go 180 degrees, we can see it matches back up. So it is that figure's rotational symmetry. Then we can go 270 degrees. Again, that figure does not match up with those lines. So that is not a rotational symmetry of this figure. And again, if I go at 360 degrees, well, then it does match up again. So that is, in fact, a rotational symmetry of this figure. Okay? 1 second. So, okay. So the rotational symmetry of a geometric figure is the characteristic of a figure to map onto itself through the center of rotation. The number of rotations that map a geometric figure onto itself is called the order of rotational symmetry. So here we have this rectangle. If I turn this rectangle, about that center point, 45 degrees, let's say, we can see that that rectangle does not map back to its original point. So that is not an order of its rotational symmetry. If I go ahead and go 180 degrees, well, we can see that that rectangle did map back to that point where it started, and so that is an order of rotational symmetry. So we can say that this rectangle has 2 orders of rotational symmetry, one at 180 degrees and one at 360 degrees. Every figure, no matter what it looks like, has a rotational symmetry at 360 degrees. So every figure has at least one order of rotational symmetry. The reason being, if you turn any object 360 degrees all the way back around, it would obviously map back to where it originally was. So every figure has a rotational symmetry of at least one. Okay? Is there any questions? Any questions? And so here we're going to look at the rotational symmetries of these trapezoids. We took this trapezoid and turned it around. What we would find that it only has one order of rotational symmetry at 360 degrees. Again, every figure has at least one order of rotational symmetry at 360 degrees. Same thing with this trapezoid. The only instance in which we can turn it around and it'll map back to where it originally was is at a 360 degree rotation, so it has one order of rotational symmetry. Any questions? No? Okay. And so same thing for rotational symmetry as is in reflectional symmetry. Regular polygons with n equal sides will have n rotational symmetry. So this is a regular polygon. This regular polygon has 3 sides, and so we can say it has 3 order of reflectional symmetry. Very similar to reflectional symmetry. So this one has 3 order of rotational symmetry and 3 order of reflectional symmetry. We know that because of the number of sides of this regular polygon. There may be some instances in where you're asked to find what is the smallest measure or the smallest angle that we can rotate this triangle for it to map back to itself. Well, the way to answer that question is to put it into this equation. So 360 divided by n. N being the number of sides, we have 3 sides, and so we get 120. 120 is the smallest angle measure that you can turn this triangle in order to get it to map back onto itself. And if you want to find, okay, we know that this triangle has 3 orders of rotational symmetry. What are those 3 orders of rotational symmetry? Well, we know one is 120. Well, if we take 120 times the one side, we get 120. 120 times the second side, 240. And 120 times the third side, 360. And so there are 3 instances in which that triangle will map back onto itself. When we do a rotation of 120, a rotation of 240, and a rotation of 360. Okay. And so here we see this again. For regular polygons, the order of rotational symmetry is equal to the number of sides. And you can find the smallest angle of rotational symmetry by doing this equation. So here we have a regular polygon, which is an octagon, or a hexagon. I keep saying octagon. Hexagon because it has 6 sides. 1, 2, 3, 4, 5, 6. Okay, well, because it has 6 sides, we can say it has 6th order of rotational symmetry. And if we want to find the smallest instance in which we can rotate this hexagon to get it back to where it originally was, well, we do 360 divided by n being the number of sides. 360 divided by 6, 60. So 60 is the smallest degree in which we can rotate this hexagon to get it back within this bounds. Okay? And so if we want to find out, okay, we know we're supposed to have 6 orders of rotational symmetry. Here we have our smallest order. Well, how do I find all the other measures? Well, you take 60 times 1, 60. 60 times 2, 120. 60 times 3, 180. 60 times 4, 60 times 5, 60 times 6. So here we have the 6 instances in which we have an order of rotational symmetry. Is there any questions? Any questions? So here we have a regular polygon. And so what is the reflectional symmetry of this regular polygon? Can someone tell me? If we know this is a regular polygon, then what is the reflectional symmetry? We're looking for a number. How many lines of symmetry does this regular polygon have? If we know it's a regular polygon and we know it has 5 sides, 1, 2, 3, 4, 5, what is the reflectional symmetry I'll wait for one person in the chat box. We know it's an irregular polygon. We know that the reflectional symmetry of a regular polygon is equal to the number of sides. We know I have 5 sides, so what is the reflectional symmetry? What do you guys think? Wait for one person in the chat box. One person. You can take a guess, guys. You don't have to be 100% right. I'll go over it. One person. What is the reflectional symmetry? The reflectional symmetry is the first thing we went over. We know the reflectional symmetry is equal to the number of sides. We have 5 sides. So what is the reflectional symmetry? Waiting for one person. If the reflectional symmetry is equal to the number of sides, we have 5 sides. What is the reflectional symmetry? I need one person to respond. Yeah, like the number. What number? How many? How many lines of symmetry would that regular polygon have? 1. Well, we know that the number of reflectional symmetry is equal to the number of sides. We have 5 sides. 1, 2, 3, 4, 5. So we would have 5 reflectional symmetry. So the number of reflectional symmetry is equal to the number of sides. We have 5 sides, so 5 is our answer. How about rotational symmetry? We know that for a regular polygon, rotational symmetry is equal to the number of sides. So what is the number of rotational symmetry? One person in the chat box. We're looking for a number again. One person. What is the number of rotational symmetry? If rotational symmetry is equal to the number of sides, what is, Naomi says 5. Oops. And yes, it is 5. Order of rotational symmetry is 5. If we want to find the smallest order of rotational symmetry, we would put it into this equation. 72 is the smallest rotation we can do on this figure to get it to map back to where it is. And here's all the instances in which we can rotate this figure to get it to map back to where it is, originally was. Okay, so both reflectional symmetry and rotational symmetry are equal to the number of sides of a regular polygon. Any questions? No? Okay. So what did we learn today? We learned about reflectional symmetry and rotational symmetry. Reflectional symmetry is basically the lines of symmetry that we already know. a figure maps onto itself across a line of symmetry. That's the type of symmetry we are familiar with. And then we know regular polygons have n-fold symmetry, where n is the number of sides. So if we have a triangle, which is a regular polygon, a triangle has 3 sides, and so it has 3-fold symmetry. Rotational symmetry, on the other hand, is a figure which maps onto itself about a center of rotation by a certain angle measure. So if we have to rotate that angle, and we're trying to rotate that angle until it matches back to where it originally was. And regular polygons have n of rotational symmetry, where n is the number of sides. So again, if we have a triangle has 3 sides. So we know that a triangle is a regular polygon, and so that triangle has n of reflectional symmetry. Is there any questions? No? And I'm going to show you one more example, just to make sure we're clear. Okay. So let's see. Let me get a bigger paper, 1 second. Oops, 1 second. Okay. So here we have a square. And I'm going to map where that square originally is by just drawing a dotted line. Okay. So we have a square. We know that a square is a regular polygon. How is a square a regular polygon? Well, because if we have a square, then we know that all the angles of that, all the angles of that square are the same. They're all equal to 90 degrees. And all the lengths of that square are the same. So this is a regular polygon. A square is a regular polygon. Okay, so when I'm being asked to find the reflectional symmetry of that polygon, of that square, well, I know that this square has 1, 2, 3, 4 sides, and I know that it's a regular polygon. And so the reflectional symmetry is equal to the number of sides, so we have 4-fold reflectional symmetry. Right? Okay. Now for rotational symmetry. Here we have the figure r square. We know that because this square is a regular polygon, it has 1, 2, 3, 4 sides. We know it's a regular polygon again. Well, we know that regular polygons, their rotational symmetry is equal to the number of sides. So this square would have 4 order rotational symmetry. Okay, we know this because if it's a regular polygon, the rotational symmetry is equal to the number of sides. Well, if we want to see this, what we can do is go ahead, we can turn the square 90 degrees. So I'll turn it 90 degrees. Well, look, it maps right back onto where it was. I'll turn it again 180 degrees. And there again, it maps back onto where it was. I'll turn it 270 degrees. Again, it maps back where it was. And then I can turn it again 360 degrees, and it maps back onto it was. So there are 4 instances in which I can turn this square to get it to be rotational symmetry. Okay? And if I wanted to find out, okay, well, we do in fact have 4 order of rotational symmetry, 4 instances in which I can turn this square to get it to map back to where it was. If I want to identify what is the smallest angle that I can turn that square in order to get it to map back to where it was, well, I'll put it into the equation. 360 divided by n. N is equal to 4. 360 divided by 4. We know n is equal to 4 because n is the number of sides. 360 divided by 4 is 90. So the smallest instance in which we have rotational symmetry is 90 degrees. We know we need 4 instances, so how do I find those 4 instances? Well, 90 times 1, 90 degrees. 90 times 2, 120 degrees. 90 times 3, 270 degrees. And 90 times 4, 360 degrees. So those are my 4 instances of rotational symmetry. And I showed you that. Again, if I take this figure, rotate it 90, yep, that's a type of rotational symmetry. Take this figure, rotate it 180, yep, that's a rotational symmetry. Take this figure, rotate it 270, and rotate this figure 360. Okay? Is there any questions? No? Okay. Here are the terms we went over today. And here's how we answered the question that we started with. Symmetry is shown when a figure maps perfectly onto itself. We can identify the lines of reflectional symmetry as well as the angle of rotational symmetry. Regular polygons have n-fold reflectional symmetry, where n is the number of sides. And regular polygons with n equal sides will have n order of rotational symmetry. Is there any questions? So here's what's due. Please do the do now if you haven't done so already.